Many thanks, Ivan, for the introduction, and many thanks to Carlos and Alex for their enduring effort in organizing workshops in such difficult times. And it's a pleasure for me to give you to try to give you some ideas on the experimental studies of the fundamental properties of supersolids that we are performing in a dipolar quantum gas. Let me start by introducing the team, the fantastic team that is working with me. So Nicolò Antolini and Giulio Beggioni are PhD students. Luca Tanzi is a junior researcher, and then Andrea Ferretti and Carlo Gabbanini, senior researchers in the new laboratory in Pisa, where we are studying dipolar supersolids. So what is a supersolid? A supersolid is formally a system, a quantum system that breaks spontaneously both gauge and translational invariance. In the simplest case, which was the one first brought on by Eugene Gross more than 50 years ago, you might think of a supersolid as the system which has a macroscopic wave function with a well-defined phase phi as in a standard superfluid, but with a periodic modulation of the density as in a solid. And thanks to this combination of superfluid and solid properties, the supersolid is expected to have a totally new set of properties compared to both superfluids and solids. As you can see here, the first proposals are from more than 50 years ago, and in the last decades, in these 50 years, there have been lots of effort at an experimental level to spot supersolid-like phases. And there are now recently, actually, many systems starting from helium-4, helium-3, superconductors. It is known that there are supersolid-like phases in neutron stars, and there have been observation of supersolid-like phases for ultra-cold atoms in optical cavities or with the spin-on recoupling, and there have been many theoretical proposals for many systems, including many quantum systems based on quantum gases. There are many systems for which there are at least some partial indications that superfluidity might coexist with a breaking of the translational invariance. The particular system that we are studying is a strongly dipolar quantum gas. So we have a gas of ultra-cold bosonic atoms, in our case of dysprosium atoms, which has a rather large magnetic moment. And the fact that the magnetic moment is associated to both a repulsive and an attractive interaction with this anisotropic structure gives rise to a very interesting property. Once you take your ultra-cold gas, you subject it to an external magnetic field, and you bring it to a regime where the dipolar forces dominate over the repulsive contact forces. In this case, if you would have a system in free space, the energy would be minimized by putting all the dipoles one on top of the other. We have a trapped system. And so once you have a system in the trap, you cannot realize this very long configuration, but it tends to break up the system in pieces. And so in between this configuration depicted here at the bottom, which is the so-called droplet crystal, and the standard Bose-Einstein condensate, some years ago, we discovered a very tiny but very interesting regime of interactions where the system develops supersolid properties. These quantum, so this is a very basic, very intuitive explanation of the phenomenon. Actually, the supersolid lives thanks to the competition between dipolar interactions, contact interactions, and also quantum fluctuations. But this can be thought as the quantum version of the different type of systems, which are the classical ferrofluids that are known since many years, that show a similar behavior under the action of an external magnetic field. So the several supersolids have been observed for the first time by my group and two other groups in Innsbruck and in Stuttgart 3 years ago now. And so far we have been studying the basic properties like the coherence using matter wave properties, the spontaneous breaking of the two symmetries. This is the work that we did with the group of Alessio Zingari and Alessio Recati and Sandro Zingari in Trento, that demonstrates that the supersolid has also a solid-like nature. During this talk, I will report on a more recent study that we did still in collaboration with the Trento group, aiming at spotting the superfluid properties, the non-standard superfluid properties of supersolids. But before going to superfluidity, let me start by another type of study that we did more recently. So here there is, as you can see from all these experimental plots, we have typically a system that can be controlled going from a standard Bose-Einstein condensate to a supersolid. And so the first question to ask actually would be, what is the character, what is the nature of this quantum phase transition between a superfluid and a supersolid? So let me talk of this quantum phase transition. And first of all, that we mentioned that for the study, what we study is so we typically have a rather small and elongated supersolid, like in this simulation here, but we look at the supersolid after a time of flight. So essentially, we look at the interference of the matter waves originating from the sides of the supersolid lattice. And from observables like the contrast or the phase of the interference, we deduce the properties of this supersolid. Our main observable for the quantum phase transition, as you can imagine, is the contrast. The contrast is different from zero in the crystal-like in the supersolid phase where there is a density modulation, and is identically zero in the standard superfluid regime, where the density is instead homogeneous. And so here one can draw some theoretical expectations looking at the basic Landau theory. And in particular, so everybody knows that if you take a one-dimensional system where a crystal-like structure develops, then due to the symmetry of this one-dimensional system, you can have only even terms in the free energy expansion. So you can have only a second order or continuous phase transition. While if you go on a two-dimensional system like this blue part of the graph here, and you have a triangular type of lattice, like it is expected for a dipolar supersolid in 2D, then the transition becomes of first order, so discontinuous, because there are also odd energy terms in the free energy. So the question is how this general theory applies to the specific case of a trapped Bose-Einstein condensate, the superfluid, making a transition to the supersolid phase. So here is the answer that we got from a numerical simulation that we did with the group of my brother Giovanni Modugno in Bilbao. And what I'm plotting here is essentially the character of the transition, whether discontinuous or continuous, as a function of the experimental parameters, which are the atom number and the transverse trap frequency. So essentially, we have a system where all the trap frequencies are fixed, but we can only vary the atom number or the transverse frequency. And we can study the evolution of the contrast as the function of the scattering length for each set of parameters, and we can see whether the transition is continuous, like in this red case, or is discontinuous with a jump in the order parameter, like in the blue case. And very interestingly, we find two different regions of discontinuous and continuous phase transition that are accessible experimentally. And so the answer is why? How does it turn out that this system has both continuous and discontinuous phase transitions? How do they relate to the general theory for 1D and 2D systems? And the answer is that there is a very interesting relation that this continuous type of transition is associated to 1D supersolids. The discontinuous type of transition is associated to 2D supersolids, but there is a very interesting variation with respect to standard system that is related to the fact that these are not real solids. Here, there is not one particle per site. Here, in each site of the lattice, there is typically a few thousand atoms. So this is a cluster solid. And when you have a cluster solid and you compress it, like here, so you can think of going from this picture number 1. This is a clearly two-dimensional solid which shows a discontinuous phase transition. And if you make a Fourier transform, you can clearly see that there is an hexagonal shape in momentum space, which means a triangular shape in real space. So this is a two-dimensional system, discontinuous phase transition. And then when you compress your trap and you go, for example, to this case number 2, this looks a lot like a one-dimensional system. But once you make a Fourier transform, you discover that there are still some side peaks in the Fourier transform, which means that here in real space there is a very small but important triangular background of the density. So the background density has a triangular structure. So despite that the system looks 3D, looks 1D, it is still 2D. And so here, only going to very, very strong confinements, the system loses its triangular structure and becomes really one-dimensional. So there is a continuous crossover from two-dimensional system to one-dimensional systems. That is a peculiar property of this cluster type of solid. That is the supersolid. We could verify this theoretical prediction by looking at the experiment. There are various ways of checking that there are both for two different types of traps, this blue one and the red one. The transition is clearly discontinuous in the first case and continuous in the second case. We can see it by looking at the behavior of the energy. So the adiabaticity of crossing the transition in one direction first from the superfluid to the supersolid and then back to the supersolid. If you cross it for this red trap, then there is no energy release. So it really seems that we can cross it adiabatically, while for the blue trap, there is a big jump in the energy when going back. And we associate it to the discontinuity of the transition in this second trap. Very interestingly, if we look here for the discontinuous transition, there are rather strong fluctuations in the contrast, and so we decided to look at the fluctuations because from the fluctuations one can also get information about the character of the transition. And indeed, if we take our evolution of the contrast with these fluctuations for both the continuous case, the supposed continuous case and the supposed discontinuous case, so red and blue, and then we divide it into regions, and then we look at the distribution of fluctuations and the distribution of contrasts, then we can clearly see, look at these two panels number 2. So that for the red case in this region 2, there is a single maximum of the contrast, while there are two different maxima of the contrast in the distribution for the blue case, for the discontinuous case. And this is indeed consistent with having a single minimum in the free energy for the red case and two minima in the free energy for the blue case. So what happens in this case too is that in each repetition of the experiment, we populate either this minimum at 0, which means the superfluid, or this minimum of the free energy at large contacts, which corresponds to the supersolid. So this is an additional evidence of the fact that there are two different transitions that can be controlled by simply changing parameters like the atom number or the trap frequency. This result is very important in the context of dipolar supersolids, because this is the first time that the continuous transition is spotted in an unambiguous way. And as we'll discuss at the end, this is very important to create excitation-free supersolids. Now, let me come to the second subject of this talk, which is superfluidity. And in particular, what we studied is superfluidity of the supersolid under rotation. So here there is a collection of results for the rotation of various types of superfluids. So here, what is plotted in all cases is the angular momentum as a function of the rotation frequency of the container that contains the superfluid. And as you know, both for helium-4, helium-3, or BECs, this is particularly visible for BECs. This is a result for the group of Landau. So when the rotation frequency is small, the angular momentum is 0, and it becomes larger from 0 and actually multiple of h bar only when you create vortices in the system. The region we are interested in is this low frequency region. What happens here is that thanks to the irrotationality of the velocity field combined with the homogeneity of the density of the system, the only possibility, the low energy state for the system corresponds to having the superfluid at rest in the laboratory. So your container is rotating, but the superfluid is not rotating. So the angular momentum is 0. What happens, and there are, of course, as you know, similar effects in superconductors. How does this picture change in a supersolid? Well, this was studied many years ago, 50 years ago, by Anthony Leggett. What he found is that the behavior of a supersolid is intermediate between a standard solid and a superfluid. So the configuration that he considered is this annulus, and that is rotating with some frequency. So this is the container. It's an annulus. It's a torus that is containing your system. And well, you know that if you would have a classical solid, then the density of the classical solid is like this. So you have well separated, distinguishable density, maxima in the density, and so the rotation happens classically. So the system rotates, and the moment of inertia is the classical moment of inertia. If you take a standard superfluid with a constant density, like here, then, as I was saying, thanks to the irrotationality, the only possibility is that the superfluid is at rest, and the moment of inertia is 0. The results by Leggett was that for a superfluid, where you sort of have both components, because again, your density is this light blue. Is as this in light blue. So you have some modulation of the density, but also some common background like in the superfluid. And what he found, by simply minimizing the energy, actually the calculations are not so simple. That's why I'm trying to simplify for you the results here. What he found is that the moment of inertia is intermediate between the two cases. And he found that one can define a superfluid fraction that has at the end a very, that is found by a process of minimization of the energy, and at the end it has a very simple relation with the distribution with an integral of the inverse density of the system. So this superfluid fraction is peculiar of supersolids. This is different from zero even at zero temperature, and can change in principle from zero, and then you would have a normal solid, or one, and then you would have a superfluid. To test these properties, we have performed an experiment that was studied theoretically by the Trento group. This is the scissors mode. So we do not have an annulus so far in our system. So what we did, we took our elongated system in the harmonic trap, and then we put the harmonic trap under oscillation by creating an angular excitation. And then we follow the evolution in time of the angle of the distribution, both in the superfluid and in the supersolid case. In both cases, we see a nice oscillation of the angle with one single frequency. And it is very interesting what happens when we compare these measurements of the frequency with the theory, and in particular also with the simulations by the Trento group. So in this upper panel here, you can see the evolution of the frequency when going from the BEC to the supersolid. You can see that the oscillation frequency is almost constant in the supersolid, and there is a jump and a quite drastic change of the frequency in the supersolid. And it's possible to relate this frequency of the supersolid to the moment of inertia of the system through this formula that was derived by the Trento group, that can be thought as an evolution of the simpler formula that is used, that defines the behavior of the famous torsional oscillators that have been used many decades in the solid helium to try to spot a supersolids. So essentially, from the frequency and the knowledge of some geometrical properties of the system, you can derive the moment of inertia. And you can see in the bottom panel that while the moment of inertia divided by the classical moment of inertia, so this is the relative moment of inertia, for the superfluid is clearly different from one. It is clearly non-classical. When you go to the supersolid, the moment of inertia tends to increase, tends to go closer to the value of one, which would be the moment of inertia of the standard solid. This even intuitively gives evidence of the fact that the supersolid has a moment of inertia that is intermediate between the one of the standard BEC and the one of a standard solid. Then, of course, this is a very simple explanation, a simple discussion, simple analysis of the results. We could make a more refined analysis by deriving directly the quantity, the superfluid fraction. So in these elongated systems that are not in an annulus, the definition of the superfluid fraction is somewhat more complicated than in a circular geometry. There is this extra term, but in any case, it is possible from the measure moment of inertia to derive a superfluid fraction. And very interestingly, the experimental superfluid fraction, these red points, are consistent with 1 for the superfluid, and is perhaps tends to become smaller than 1, although the error bars do not allow us to tell it that it's really smaller than 1 for the supersolid. So the supersolid has a smaller superfluid fraction than the supersolid, than the superfluid. Here, actually here, if you try to compare the results, the experimental results or the simulations by the Trento group, where we tried these black dots, with the superfluid fraction derived by the Leggett calculations, which are these open triangles, there is not a very good quantitative agreement. So in both cases, there must be a decrease of the superfluid fraction, but there is an offset between the two. Actually, what we found is that most of these offset can be explained by calculating the contribution to the superfluid fraction coming from the rotation of the individual droplets of the individual sites in the supersolid. That is something that was not contained in the theory by Leggett. So this is not a quantitative calculation, but intuitively we can think of the superfluid fraction of the droplet coming from some more trivial effect, which is each droplet is a Bose-Einstein condensate, very in brief, and the superfluid fraction of the supersolid coming from the Leggett mechanism. So then there was recently some criticism or some open question by the Innsbruck group about the possibility in general to measure the superfluid fraction a la Leggett in these trapeze systems that have a very different geometry from the annulus that was proposed by Leggett. But so we performed some detailed analysis of the numerical simulation. So what you can see here, this is a cut in the density of our supersolids that is performing the seesaw oscillation. So you can see the angular oscillation. So you can see the two central droplets like here, and then these two side lobes that are these side small droplets. So as you can see, there is a very interesting contribution to the motion that is coming from this outer ring. So there is a ring of even smaller droplets that are not visible in this cut of the density, but they are visible in the two-dimensional simulations. And so what we think is that this contribution here to the moment of inertia, or if you want the excess of the superfluid fraction with respect to the one coming from the individual droplets, is coming exactly from the rotation of the superfluid of the supersolid along this type of ring that is very similar to the Leggett situation. So I'm coming to the end of my talk. We have, I hope that already these simple examples of what we can study in the supersolid can convince you that these are very interesting systems. These are, so far, we are studying mainly the superfluid properties of the system. So we are taking our system and trying to compare our supersolid and comparing it to a standard superfluid. And we are finding new properties, like, for example, these superfluid fractions. More recently, we have been studying, so we have a list of things on our agenda that we think are very interesting. At the moment, we are studying the Josephson effect. This is a system that has a natural structure like a Josephson junction, or better, a set of Josephson junctions that are, however, not set by an external potential like in standard Josephson junctions. And so this is a very interesting phenomenon that we are studying right now in the lab. I have no time to explain you what we are seeing. But I hope we can come out with a paper soon. The possibility of crossing a second-order phase transition is very interesting because it opens an interesting direction to study the entanglement properties of the supersolid. So this is a quantum phase that is reached by through a spontaneous symmetry breaking. So there is a general expectation for the presence of entanglement. Other interesting new directions are the study of persistent currents, vortices, and so on. Supersolids, maybe this is more for the future, but let me mention that the supersolids can be seen also from the point of view of solids. And so here, a very interesting property that would be that we are very interested in studying is the possibility of creating deformations in the solid without dissipation. This is something, of course, impossible in a standard solid, because to create deformation, you have to move distinguishable atoms from one side to the other, or similar. In the superfluid, you can move in the supersolid, you can move in principle a part of a lattice relative to the other one, and if you do it in an adiabatic way, you should be able to achieve a deformation without dissipation. So a superfluid behavior of a solid. So this is everything I wanted to tell you in this brief introduction to supersolids, and so thank you very much for your attention.
Thank you very much, Giovanni. Okay, so we have time for questions. In the audience room first.
Anyone from the audience?
So I would like to ask the question, Piotr Magierski. The question is there any characteristic temperature for these structures to appear, above which these structures disappear?
Many thanks for your question. So this is something that has been studied. So there is a first study by the group of Francesca Felleino in Innsbruck, where they studied a transition from a normal gas to a supersolid. Not passing through, they are going to the supersolid through a classical phase transition by changing the temperature, and not to the quantum phase transition like we do. What they see, and that is also consistent with what we see in our experiments and in Stuttgart, is that the supersolid is very robust. So the superfluidity in the supersolid is very robust, even if the temperature is, so the temperature doesn't need to be incredibly low. This is because, let me go to any of the pictures of the supersolid, or let me go to this sketch here. So this is due to the fact that the link between the different sites in the supersolids are, or in the supersolid, these links are, at least in some regimes of interactions, are very, very strong. And so thermal fluctuations are not, the thermal fluctuations at the typical temperatures of the temperature of the supersolids, which is a few tenths of nanokelvin, are not able to destroy the coherence. So this is the only general thing that I can tell you, because so far a detailed quantitative study of the temperature dependence of the coherence properties and all the other properties of the supersolid is missing.
So there are other questions. There was a question before you. So.
Hi, this is Neil Warrington from the INT. I'm just wondering, are there critical exponents for this phase known?
Thank you very much for your question. No, not yet. This is one thing that we wanted to measure. We have not tried yet. If you want, the expectation is that the mean field critical exponents should give a good approximation of the critical exponents of the system, meaning that this system is quite well described by a Gross-Pitaevsky mean field theory. This is the only thing that I can tell you so far. But this essentially is something that would be interesting to measure in the experiments.
Hi, Giovanni. Sandro. Raising a comment and a question, which is at the same time comment and a question. In the recent paper that you mentioned by the Innsbruck people, and in the paper that we recently published, we understood that the moment of inertia can be calculated, but this requires a measured experimentally, in principle. But for this, you should be careful in the identification of the scissors mode. So the scissors mode is not always a single frequency mode, but you have a structure of excitations which is sort of complex to investigate, but it's possible, at least theoretically. And so the question whether the system can be identified as a superfluid is a very clear answer, and this is positive, but and the moment of inertia can be measured and calculated, but this requires a careful analysis of the scissors mode.
Thank you, Sardo. Thank you. Yes, thank you. And let me mention in response to your comment. So we did this work basically together, but this is for the rest of the audience. It seems that only in these very small systems like we have here in the lab, so very, very small, the scissors mode is essentially only one frequency. Is it correct?
So I don't know whether this is the complete answer. I think it's important system is very elongated, mainly. But now this is more technical questions for specialists.
Thank you.
Altre domande, other questions? Maybe people online have questions, but can they manifest themselves some way?
I have a few, but I was going to ask Giovanni, you're going to be around for the discussion session, Giovanni, because I don't want to take the time for other people.
Okay.
Yes, yes.
Are you going to be around for the discussion session at the end of the day?
Yes, I will be there.
Okay, so then I'll ask the questions there. Sorry.
So
people from the
I think
audience.
Thomas Pappenbroek has a question.
Yeah, please.
Oh, thank you for the nice.
Okay, please ask. Yes.
Yes, I just wonder. So, what are the Nambu-Goldstone bosons here? Is it phonons like in a solid because to break translation invariance, and or what is it here? The lowest lying excitations.
Thanks for the question. This was studied from. This was studied already. So sorry, I'm looking for the right slide. Let me see if I have a slide from our lab ready here. Okay, you can see probably from this picture. So the Nambu-Goldstone excitation, so the lowest energy excitation in this system was studied first by the Stuttgart group. This corresponds to a motion of the lattice, a translation of the lattice of the supersolid in the harmonic trap. So it has some finite energy. It is not zero energy. It has some finite energy, but you can see here from this data here. So these are different repetitions. These on the x-axis there are the repetitions of the experiment. On the y-axis here in blue is the position of the maxima, and you can see that each time. So this was a three-site supersolid. So each time there is a different position of the maxima, but as you can see from this right panel, the central mass doesn't move. So this Goldstone mode is an oscillation of the position of the peaks or of the phase of the lattice, if you want, but without a motion of the central mass. And so it has a quite low energy, just a few hertz.
Okay, thank you. I'm sure there are other questions, but I think we have to go on.